Okay, so hello and welcome. This is the How To Talks by Postdocs. This is our final talk in our fall series. Today we are very excited to have last season's VCU Science Communication Award winner, Dr. Sean Koebley, and he is here to talk to us about Bayesian statistics. So Dr. Koebley is an IRACTA alum. He's a postdoctoral fellow in Jason Reed's lab in the physics department, researching a novel method for detecting genetic mutations using biophysics. Formerly, he taught middle school mathematics in Boston and Washington, D.C., before earning his Ph.D. in applied science from the College of William and Mary. Okay, so take it away, Dr. Koebley.
All right. Thanks, Stacy. And hi, everybody. It's great to be with you here today virtually. And I'm really excited to share with you some Bayesian statistics today. This is a talk I gave back in the spring and got some good reception. And I'm hoping, it's going to look very similar today, but there are some things that I tweaked and added as well. Hopefully just to clarify and bring home some of these main important topics. So let me share my screen here so we can get started. All right, hopefully that's good. Okay, yeah, so we're gonna be talking today about this alternative statistical framework that you may have heard about, Bayesian statistics, that can be a replacement of frequentist statistics, which involves null hypothesis statistical testing and the p-value, which is most commonly used in scientific labs and experimental design. So we're going to talk about some of the strengths, disadvantages of p-value, and then talk about the basic fundamental framework of Bayesian statistics, and then do a practical example. But before we get started, I just want to establish some norms for this talk. I want this to be as participatory as possible. So if you have any questions, feel free to chime in and just ask them while I'm talking, and we can hopefully get to them. I did leave some time for questions. We'll also have some time at the end. Yeah, just again, in the spirit of this being as involved as possible, there's going to be definitely some parts where we want to have pen and paper or pencil and paper on hand. We're going to be doing some very minor algebra, and they're just trigger warning. There's going to be some math, a little bit of math here, but nothing. Hopefully, that's too intimidating. Also, this took me a few times to get this stuff, so don't worry if you don't get it 100% the first time. I'm going to give you plenty of resources that you can look into, a few papers, and then a few textbooks that you can check out to really hit this stuff home. This is meant to be a basic introduction that should be, it should give you a good start. So with that, let's go over our aims. So by the end of this talk, hoping that you'll be able to describe the limitations of frequentist statistics, which is the p-value and null hypothesis significance testing, derive Bayes' theorem, and intuitively describe its terms. There's some new vocab that we're hoping to learn. That's big here, learning some of the important vocab the surrounding Bayesian statistics. And then we're going to use Bayesian inference in a practical example to determine if two normally distributed groups have credibly different means. And finally, just throughout, I'm going to be giving you some references that you can refer to. And at the end, I'm going to give you all the code that I used to do this practical example. Or I think that'll come maybe in a week or something after this presentation. So just keep an eye out, and you'll actually be able to do this, test this yourself with step-by-step instructions. So we're going to start with frequentist statistics, probably what most of you are familiar with. And I like to do this with a favorite comic of mine from XKCD. And it starts with a researcher with a hypothesis who says that jelly beans cause acne. And so the lab investigates and they find no link between jelly beans and acne, and they find a p-value greater than 0.05. They say, all right, that's it. But the researcher says, well, wait a minute. I think it's only a certain color that causes this. So they go back to the lab and they test out 20 different colors. And what do you know? In one of those cases, they find a p-value less than 0.05 for their experimental test. And so this is big news that, in fact, green jelly beans do cause acne with 95% confidence because that p-value was less than 0.05. So I guess I could just open it up here. Can anybody explain this joke, or why is this possible that this might happen? Or what does this mean, that we have 5% chance, only 5% chance of coincidence as listed in this newspaper? Does anyone want to give this a shot? Explaining the joke.
Would sample size have anything to do with this?
Actually, in this case, it's, they don't really give an example of the sample size for each one of these tests. I guess we could assume that for each one of the colors, they're using the same number of participants to see if acne is being caused by a diet of jelly beans. But that's actually not, that is definitely one thing you have to really pay attention to in null hypothesis significance testing. But in this case, it's not really part of the design that's mentioned here.
How about the 5% significance level used there means that there's a 1 in 20 chance of a false positive.
Right. Yeah, that's kind of what they're getting at here, that when we say a p-value less than 0.05, where intuitively that kind of means that if we were to repeat this experiment 20 times, one out of those 20 times, we'd expect there to get a true result. In this case, the true result being that jelly beans cause acne, just by random chance. That's what the p-value of 0.05 kind of means intuitively. And so that's what, if you do this test 20 times with different colors, you're just going to get one of those results being a false positive if you're going by that cutoff of 0.05 for your p-value. So that's one of these things you got to be very careful when you're interpreting the results of a null hypothesis significance test. And what's interesting is that, that single test for the green jelly beans itself, there may not have been anything wrong with that test, but the intention of the entire test, the whole sphere of your test here, affected your actual result. Because you've tested 20 different colors, it's kind of affected how you interpret these results. So I think that's interesting, and that's one of the issues with p-value maybe in one case. But let's see if we can drill down using this example and come up with a more formal definition of what the p-value is. So this is something maybe I want to give you 30 seconds to maybe write down on your piece of paper. See if you can, using this example, what's the definition of the p-value in general? If we say, for example, if a test yields a p-value of 0.05, given a null hypothesis that the green jelly beans don't cause acne. Our null hypothesis is kind of like our starting point. But yeah, what would you say the definition of the p-value is? I'll just give you around 30 seconds, right on your own, and we'll bring it back in a second. Okay. We got any brave souls out there and want to give this a shot?
I think I've been poked by a professor. It's the probability
Nice.
of rejecting the null hypothesis when the null hypothesis was correct. So you have a 5% chance of rejecting green jelly beans don't cause acne when that was correct.
Yeah, I think that's definitely getting there. Probability of rejecting the null hypothesis. I think what we need to do is be a little more specific, or talk about how we can bring in the results of the test. So you say probability of rejecting the null hypothesis. Is there any way you can bring in, the results of the test into the definition? Because rejecting the null hypothesis could mean a few different things. Does anybody want to add to that?
Maybe something like I'm 95% confidence of rejecting the null hypothesis in favor of alternative hypothesis.
Okay, so 95% chance of rejecting the null hypothesis. I think that's maybe getting a little further away from the actual meaning. And again, we're still looking for how do we talk about the results? How do we link the results of the experiment?
Could it be that, oh, sorry. Could it be that the results of our experiment showed that that the green jelly beans cause acne when in reality they don't? Something like that our results showed it.
Yeah, so what's the p-value then?
The p-value is the chance that would have happened.
That you get that result.
Yeah, that we would get that result.
Is that can we link in the null hypothesis into that? You're almost there.
Is it the probability of rejecting green jelly beans don't cause acne?
Yeah. So, well, I'm gonna kind of combine what the last two volunteers have said here. So we had the probability of getting the result and the probability of rejecting the null hypothesis. We're gonna say it's the probability of getting the result given that the null hypothesis is true. Okay. That's pretty close to the formal definition of the p-value. In fact, here it is right in front of you. It's the probability p of obtaining the observed result or more extreme results, given that the null hypothesis is true. That's what a p-value actually means. So is it the probability of rejecting the null hypothesis? Sort of, again, we have to bring in that result, that result into the definition. So this right here is our formal definition. And it's, you're not alone in not, not having 100% handle on that top of the mind. I'll fully admit, before I did this presentation, I did not have this formal definition in mind when I listed a p-value. And that's because it's not that intuitive. It's not the most intuitive way of doing experiments and describing the results. Because it's saying basically, all right, what if we did a future test that was exactly the same? What's the probability of getting this result or more extreme results given that the null hypothesis is true? That's what the p-value actually means. It's kind of dependent on this hypothetical future test that you're doing. But that's kind of the context of our example. And here's a mathematical formulation of this definition. So this is something maybe you can write down that's a little easier than all that text. It's P means the probability of everything that's in parentheses, which is X, some hypothetical future result being greater than or equal to, the same or more extreme than D, the data that you collected on your test. And that straight line means given that. So if you haven't seen that straight line in math before, it's a conditional probability. It means given that H naught, your null hypothesis is true. So again, that's maybe not the most simple, straightforward way of describing experimental results. And I just want you to be thinking about here, is there another probability that might be more aligned to the actual goal of an experiment? When you do an experiment, you're thinking about, all the parameters that you're trying to look at, maybe the mean, if it's, mean growth rate or mean effect of something. Is there some way we can, try to more align our experiment with the statistical reporting that we get afterwards. So with that, I just want to maybe go through some of the issues with null hypothesis significance testing, maybe, pretty quickly. I'm pretty sure some of us have, or most of us have experienced some of these at one point or another. This is one that we kind of just encountered, which is it can be a confusing, unintuitive, and dependent on assumptions is something separate, but most NHST that has some normality assumption. So it maybe assumes normal distributions of data in many cases for the simplest testing, which is not always the case. And when you do these tests, you can only fail to reject the null hypothesis. You can't accept it, really. That's kind of a limitation. P-value is dependent on sample size. This is a huge one. If you've heard of p-hacking, this is this unethical way of perhaps, running a test, which I'm sure we've never done, but we've always maybe we've seen news of this perhaps where you could just, if you don't get a significant result, well, I'll just do twice as many tests, and then maybe I'll get a significant result, because the larger your sample size, the lower your p-value gets. Your p-value is absolutely dependent on sample size. And here's one: p-value for one outcome is based on possible results for other outcomes. The intention of your testing matters, and this is what we saw in our example. For that one test that's highlighted in blue, you got the significant result, but that was dependent on this whole sphere of your testing strategy. So when you're doing something like an ANOVA, you actually have to account for that, and you have to do an adjustment of normality that has a lot of pretty complicated stats that go along with it. And again, it just kind of adds to the burden of complication when you're running these tests. Confidence intervals are much better than a straight p-value because it gives you, a size of the effect, but it still suffers from that dependence on intention, and it's just two endpoints. It's not actually giving you a distribution of the probability. It's just giving you maybe a lower bound and an upper bound for the confidence of an effect. And finally, this one's really interesting too. There's no prior knowledge baked into a null hypothesis standardized test. So if we start with a test, if we're saying, all right, I want to know if this coin is fair, I'm going to design an experiment. Maybe I flip it 100 times to see if this coin is fair. And I have to start with a null hypothesis if I'm doing null hypothesis significance testing. Can anybody tell me what's your null hypothesis in this case if I'm asking if a coin is fair?
P equals 0.5.
Yeah, your probability of getting heads or tails is 0.5. That would have to be your null hypothesis. Now, what if you're testing a nail where heads in this case would be the nail landing exactly on its head? In this case, you're still running a null hypothesis significance test, so you have to start with a null hypothesis. But in this case, what is your null hypothesis?
The nail landing on its head is 0.
Well, see, we have to start with the assumption that it's fair if we're trying to reject the null hypothesis. In null hypothesis significance testing, we are trying to reject the null hypothesis. So what are we trying to reject in this case?
The nail landing on its side?
Well, the nail landing on its side, what's the probability of the nail landing on its side? If we're asking if the nail is fair, what do we want to reject potentially? What's the thing we want to reject?
It's an equal chance of head or tail with the nail.
Yeah. If we're trying to reject that there's an equal chance that the nail is fair, then whatever result we get, that should be our null hypothesis, that the nail is actually fair. that the probability of it landing on its head is 0.5, which sounds crazy that you have the same null hypothesis in both these cases, but since you're asking the same question, you have to start from the same point. You have to start from the same null hypothesis. There's no prior knowledge baked into the test, which can be a really big deal if you're dealing with something like drug discovery, or building on any kind of past result, where you have some idea of how things are going to go because you have some past data to back up your test. Really, you're not starting from a point of total knowledge. Like if you're asking if a drug has an effect and you have 20 precursors of this drug, and each of those had an effect, and this drug that you're testing is very similar in chemical structure, it's not really a great test if you're asking if the drug has any, the null hypothesis is that the drug has no effect. You have a very good idea that it has some effect. So yeah, that can be a real issue when you're trying to make subtle and powerful decisions based on null hypothesis standardized testing. You just don't have any prior data baked in. So those are all the issues, but all that being said, p-value is not going anywhere. I think it's still very good that you have a deep understanding of null hypothesis significance testing and confidence intervals and how best to work with them. I highly recommend this book if you're not aware of it. It's pretty cheap, and it has just really intuitive step-by-step instructions for getting through a lot of the more sticky aspects of frequentist statistics. So huge recommendation that I give to picking that book up. Okay, so we've described some limitations. Let's see if there's a possible alternative to this, which is Bayesian statistics. And we're going to start from the very beginning with this. In Bayesian inference, I'm going to give you the definition, and we're going to walk through each of these terms one by one. We kind of think about what we're doing in an experiment in a different way. We say, we're going to do this experiment, and we're going to reallocate the credibility of the parameters theta so that we make them more consistent with the data D. So I'm just to say this one more time. We're going to reallocate. Bayesian inference involves a reallocation of credibility towards parameters theta that are more consistent with the data D. So what we're doing here is starting with prior data. First of all, we bake in prior data at the very beginning. We're saying we have some prior guess. This is a naive guess maybe, but it's something. You always start with something in Bayesian statistics that your parameters theta happen to be true. So maybe it's like a mean of 2 and a standard deviation of 3. There's just some inherent probability that that is true. If it's a normally distributed data, for instance. Then you collect your data D and you refine or reallocate your guess based on that data D to get what's called the posterior. This is your ultimate goal in Bayesian statistics, which is the probability of theta given the data D. And that's your conditional or posterior guess for what those parameters are. And that guess is inherently more informed than your prior guess because it's given the data. It's relying on the data that you've collected. And I would argue this is a much more intuitive desired endpoint of experimental inference than that definition of a p-value that we just saw, where you're saying probability of a test is, or the result of a test is more extreme than your data given that the null hypothesis is true. What we have here is much more direct. Yes, I think I have a question from Ryan.
Yeah, just on I'm trying to piece together the argument for the approach, because right now I've got that we have if I understand you correctly, we have an unintuitive approach with the p-value because we're looking at extreme cases for conditioning, but then the Bayesian approach assumes prior knowledge in the first place. So is your argument that if you know something, then you should state it up front and go Bayesian?
Yeah, I think that's a huge advantage of Bayesian of the Bayesian framework, which is that, we all know something. We all have prior data whenever we run an experiment. I think in 99.99% of the cases, you're never going in completely blind when you're doing an experiment. what Bayesian inference does is it makes that explicit. It makes your prior assumptions, your prior data explicit. And I'll show you exactly how that works when we get to our example. But you're actually saying, this is what I think the mean is. This is what I think the standard deviation is. And in fact, this is how I think this is what I think the distribution of means might be. So I think the mean is 100, but I think I could be wrong. So we'll say it goes from 100. We'll say it goes from like 80 to 120. Yeah, that's something you could explicitly state when you do your Bayesian test. And that will affect the results depending on how you construct your priors. But it's explicit, it's transparent, and people can, run the same data with different priors and get slightly different results. Or you can back up why you use that prior data. With null hypothesis significance testing, you can't bake in prior data at all. All you have is your null hypothesis. Does that answer that question, that kind of comparison?
Yeah, and that helped me follow your nail argument a lot better, so thank you.
Gotcha. Yeah, that one, I love that example because it's kind of it's a mind twister, but yeah. Okay, so this is the main thrust of Bayesian inference. You're starting with prior, you collect your data, and you reallocate based on that data what the most likely parameters are for this population that you're describing. So I'm going to try to use the same color scheme for the blue and for priors, and the green for your posterior, which is ultimately what you're trying to find. But to derive Bayes' theorem, everybody get out your pencil and paper, and we're going to do this real simple example that really gets to the heart of it. So what we're going to look at is, let's see if this works. Yeah. You know what? Yeah. Use black. So we're going to look at a bag of 100 marbles. And what I'm going to do is I'm going to describe what these look like based on two dimensions, their color and their size. And then we're going to think about, okay, what's the probability of drawing a marble of a certain color or size, just straight up. And then maybe we'll work in some conditional probability in there. So what we're doing here is just finding very logical ways of dealing with conditional probability. And you'll see what I mean by that in a second. So let's set this up. So we've got our size on the top here. And we're going to do color all the way on the left. That's going to be our rows are going to be color, size is going to be our columns. And we'll do two sizes. We'll do small and jumbo, two different marble sizes. I just watched Squid Game, so this is why I had marbles on the mind. And our colors will do, we can just kind of fill in our columns here. And for colors, leave a little bit of space if you can between the color and the edge of your border. We'll do red, we'll do green, and we'll do, oops, actually wanted that to be blue. Ooh, sorry. And then green is the last one. Okay, so since we're just trying to find some really fundamental conditional probability proofs here, I'm going to decide that our size is going to be our theta variable, our parameters, okay? We're going to say that small and jumbo are our two parameters in this case, okay? And we're going to call color our D, or our data. Why is color data and why are size parameters? Because I put them that way. We could switch them easily. What we're doing with this example is just trying to get a relationship between two variables using conditional probability. Okay, so in that with those definitions, we're going to call small our theta 1 and jumbo theta 2. And we're going to call red D1, blue D2, and green D3. Okay. And then I'm just going to fill in some numbers here. So we're going to say there's 10 small red marbles. So the probability of drawing a small red marble is 0.01, because there's 100 marbles in there. So we got 10 small red marbles. There's only 2 jumbo red marbles, so that's 0.02. There are 25 small blue marbles. There are 18 jumbo blue marbles. And there are 20 small green and 25 jumbo green. Okay. That's my 100 marbles. And now I'm going to introduce a vocab word that you'll see a lot in Bayesian statistics, which is marginal. Okay. We're going to say, we're just going to sum up each of our rows here. And so that's going to give us the marginal data for each one of our D variables. Okay. Marginal just means kind of the sum of the probability for whatever variable we're talking about. Okay. It's like the total. So in this case, I'm just going to add up 0.10 and 0.02 to get 0.12. So the probability we could say of drawing a red marble is 0.12. That's your marginal data. I'm going to sum up here to get 0.43. I'm going to sum up here to get 0.45. That's what we call our marginal data. And here, do the same thing with our theta parameter. Get our marginal theta. So this is 0.55 and 0.45. Any questions about this so far? Cool. Yeah. All right. So now let's start asking some questions. Okay. And we're going to use some, math language to do this. So what I'm going to ask first is, what's the probability of getting a small blue marble? And when I say that, probability of getting a small blue marble, I'm going to ask, what's the probability of it being small? So theta 1, I'm going to use an and symbol, say it's small and it's blue, which is D2. So does anybody want to give this a shot?
Is it 0.25 by 0.55?
What is it?
0.25 by 0.55? 0.25 divided by 0.55?
Nope, that's not it. We're just looking for the probability of you picking a small blue marble. So
0.25.
Just
0.25.
0.25. Right. In this case, it's just 0.25. Yeah, you may be thinking ahead to a question I might ask in a second. But yes, in this case, it's 0.25, and I'm just going to circle that. So that's right here. Okay. It's both small and blue. That's where it lives on our chart. Let's see here. I'm going to move over to the right side to ask my next question, which is, what's the probability of now getting a small marble, given that the marble is blue? So in this case, what I'm asking is, I'm just going to put this in math terms, what I just asked. What's the probability of getting a small marble, or theta 1, given that the marble is blue, which is D2. Okay. So that's using that straight line for conditional probability, and it changes the question somewhat. So think about it. Think about how that changes the way you might approach this. And morning, does anybody have an answer to this, or a way that you could set up this solution?
Yeah, 0.25 divided by 0.43.
That's it. Okay. So in this case, I'm going to use a different color. Maybe I should switch back. But what I think Imran did there is he said, okay, since we're saying given that the marble's blue, I'm going to focus in on this row. I'm just going to put a purple star by this. I should have done that one in purple. But that's our focus. Since we've said, given that the marble's blue, we have to look only at the blue row. We have to look only at the blue row since we're saying, given that it's blue, okay? And then out of that, we look at the case where it's small as well, which is that one we already circled. So the way we calculate this is 0.25 divided by 0.43, or that turns out to be about 0.58. Okay, so there's a much higher chance of picking a small marble, given that it's blue, instead of picking a small marble and a blue marble out of your entire bag, because you have to do that reallocation, or that focusing in on that blue row when you make this calculation. Okay, so let's do one more, and in this case we're going to say, what's the probability of getting a blue marble given that the marble is small? So I switch the order. So think about it. Does anybody have a guess as to what that might be, or how we set up that problem? It's the probability of getting a blue marble given that the marble's small. Any ideas?
0.25 divided by 0.55. So you're just taking the sum of the small column as the denominator.
Right. Since we're in this case, the given that is that the marble's small, we have to focus in, we have to reallocate based on that single column. And in this case, we have to divide our probability of getting a blue marble by the total probability of getting any small marble, that marginal theta. So in this case, we're getting 0.45. So this is, the power of this conditional probability relationship is that it's extremely robust, simple, logical, and there really is. This is the foundation of Bayesian statistics here, what we're looking at right now. If this doesn't quite make sense to you, again, at this point, I'd say, come back to this, look at it a little more, see if you can find some more examples to help kind of hit this home. Because again, this doesn't really, the first time I saw this, I didn't quite 100% get it. I had to see it a few times. Yeah, Ryan, do you have another question?
Yeah, so the question here is just relating back to the previous question, but now that we have this table to work with, would be, I suppose in hypothesis testing, we might say that the small blue marble is a fair draw. And so we would be testing the null hypothesis that the intersection probability of theta 1 and D2 is equal to 0.5. And then we would have a hypothesis test for that. I'm assuming, and this is where I want clarification, that what you're arguing here is that it's much more intuitive to condition on one of the features than it is to just null hypothesis test an intersection blindly. Am I following you correctly?
I think there's some interesting parallels you're drawing there. So, and in some ways, we're running up against the limitations of this kind of simple test where we know we have very clear probabilities for each point here. So what we can do is say, so D is the one variable that we have in common between the definition of the p-value and the definition of the posterior in Bayesian. And in this case, your data D are just the columns. So I don't know. I guess I'm having a hard time thinking about how this would look as a null hypothesis test, because this isn't actually a test. This is just a logical example, right? There's actually no data here. Remember, I could have switched D and theta. This is just kind of a very basic stepping stone to show conditional probability. There's actually no real experimental testing here. So maybe hold on to that question. Let's move on to the next couple slides, and maybe we'll get there a little better, if that's okay.
Thank you.
All right. So for this next point, maybe you can follow along on your paper, and if not, we'll get the copy of this presentation afterwards, so you can see kind of the derivation of how we go from conditional probability to Bayes' theorem. Okay. And what I'm putting up on the slide here is one of the relationships we just showed, which is, I think that one up in red up the top, P of theta 1 given D2. And I'm just putting in math language what we showed. And I'm just going to work from there. So we're just going to generalize this and say, in general, instead of just working with a single parameter or a single D, we can say this is true for, any theta or any D. And then, we know that we can do the same thing, or if we switch our rho and our switch our theta and our D, as we did in that second example, you can relate this relationship to what we showed in that green example of PD given theta. And there's something you can do here. Here's a little bit of algebra. You just multiply both sides by P of theta. And you get this relationship showing a different way to express this P of theta and D. And then we can plug that in. We can just substitute your P of theta and D into that other relationship that we showed, and then we get this very special relationship between all these variables, which is Bayes' theorem. So again, maybe this is a lot of thetas and Ds. I promise you this, if you work this out yourself, it might be a little more clear how we got here. But that at the bottom there is Bayes' theorem, okay? Where that value on the left, that P of theta given D, is what we're trying to find. That's the posterior. And that blue is just the probability of theta, your priors, without any knowledge. There's no given there. We're just saying what's our first guess for what theta is. And the special value called the likelihood, which is the switch of the posterior. It's saying what's the probability of your data given the parameters. And we'll attack that in just a second. And finally, there's this red value at the end, which is the marginal data. It's just P, it's the probability of D. And that one's a real problem. We'll get to that in a second too. But what I want to show first is that we can plug in numbers now for some of these values. And now we're going to go to an actual experiment. So maybe Ryan, this will get to your question. So we're going to say that we have data that's normally distributed. Okay, it doesn't have to be in Bayesian inference. This is one of the real advantages, is you can choose any distribution. In many cases, though, data is going to be normally distributed. And again, you can choose another distribution, but it's transparent. It's baked into the way that you calculate all these values. So normal distribution, I just put up the equation for how some data X is normally distributed with a mean of mu and a standard deviation of sigma. And I'm just going to show this in, maybe this is a way you haven't seen the result of a normal distribution, but this is what it's actually giving if you're looking at probabilities, which is we're saying what's the probability of some value X given a mean and a standard deviation, a mean mu and a standard deviation sigma. Okay, so that's a way of expressing a normal distribution. That's the equation that you can start with when you're looking at your data. And let's say we actually collect 3 data points, 5.5, 5.6, 4.2. And we say we have some example parameter set of a mean of 5 and a standard deviation of 2. Let's say we want to test out. We want to see what's the probability of getting a mean of 5 and a standard deviation of 2, given that data, right? We're trying to find the posterior. Just saying, what's the probability of theta given the data? So we can start and plug in some values. So your prior is your best guess for the probability that you have a mean of 5 and a standard deviation of 2. And let's just say it's 0.2. Maybe you think there's just a 0.2 value for those 2 parameters. That's actually very high because you only have, all your probabilities have to sum up to 1. So you'd say, all right, I think there's a really high probability that this is it. And you announce it, and then we'll see in a minute how you announce this, how you do it. But you can actually show that for your prior. And then you've got your likelihood. And for your likelihood, P of D given theta, I want you to notice how similar that looks to the definition of, or just the normal distribution. The probability of D, or in this case, X, your individual data values, given your parameter values to test. So P of D, given your example, theta values, all you do is plug in each one of those data values into the formula for a normal distribution. So I think you can see at the bottom there, we multiply each one of those because they're independent events. Just like if you want to get the probability of getting 3 heads in a row, you have to multiply 0.5 by 0.5 by 0.5. And then we get out a value of 0.0068 if you actually plug all those in to the normal distribution. So what I want to get across here is that we've gone from theoretical to now plugging in hard values for 2 out of the 3 values that we need in order to get a posterior. So that's how you do it. It's that simple. And since theta is a distribution, we have to evaluate for every desired theta. And this is really where the problem comes in. And this is why Bayesian inference hasn't really been introduced, is because before computers, there was no easy way to evaluate every theta, right? Because you have to evaluate not just a mean of 5, but a mean of 4 and a sigma of 2, and a mean of 3 and a sigma of 2, and then a mean of 5 and a sigma of 1, and a mean of 5 and a sigma of 0. In fact, there's an infinite realm of possibility in most cases. So if you want to get any sense of what's going on with your posterior, you have to test a lot of different theta values. So that's one problem. And what about P of D? We kind of ignored this P of D value over here. That's related to what the issue that I just mentioned. And we'll see that in just a second. If we want to find P of D, remember I generalized kind of our example table that we set up. And you can see P of D off to the right. And just by definition, it's a sum of all of the cells in that row. But because we have this equivalency from our Bayes theorem distribution derivation, we can actually plug in a different value for each one of those cells. So now we get a different summed value. And remember, that's our likelihood right there. And that's our prior. So we know that to get P of D, we can just use this sum of the prior times the likelihood for every single parameter value that exists. So we're actually going from 1 to infinity. We have to sum up the prior times the likelihood for every single possible parameter set, which is not possible. How do you test all these possible sets of priors? How do you do it? And maybe just briefly, I'll describe how this is done with computers, because it's a really neat little algorithm. And you can use this kind of this analogy to think about how the computer runs this code. Say you're a politician and you need to visit each island. You're not a very good politician because you represent this island chain, but you don't know how many people live on each island. And you can visit each island a number of times proportional to its population so that you actually get the most votes. But you don't know how many islands there are or how many people live on these faraway islands. You can find the population of adjacent islands. So this is kind of like our probability space, where you have all these possible parameter sets that you can test, but you can't find the population, but you can only find the population of adjacent islands. You can only basically calculate one at a time. So you do a random walk around these islands. You find the population of the current island that you're on. Let's say it's this one. Oh, that's right here. And that's just, in this case, you just multiply the prior for that current set of parameter values times the likelihood, the PD given theta. And you randomly choose a nearby island, an adjacent island I. You do the same thing. You find the population of that island I, and then you move to that island I if the population is greater, or you stay if it's less, and there's some randomly chosen number that's greater than that. So basically what this does is it says you're gonna stay on the more populous islands more than on the less populous islands. And it's gonna be nicely random. You're gonna do a nice random walk, and eventually you're gonna land on every island. So this is a computational way to basically touch infinity. And this is going to give you, if you do tens of thousands of walks, it's going to give you a number of visits proportional to the population. So this is what makes Bayesian inference possible. You have to use computers, you have to use code to get it to work. And that's how you access kind of the power of this different approach. Okay, so I'm going to move on to our example, and I'm going to use kind of a classic example. What if we've got two populations, and I've given you the data here, I'm giving you the histograms of what they look like. And classically, we would ask, if there was a p-value, we'd say there's our null hypothesis is that, there's, these have the same mean, might be our null hypothesis. We'd say they have the same mean, and we run some statistical tests to see if the means are actually different, given that null. Yeah, if we get some difference in the means that's greater than what we'd expect, given that they have the same mean. Okay, when we're doing Bayesian inference, we state this a little differently. We say, given the data, is there a highly credible difference between the mean of y1 and the mean of y2? And another way of putting this is we say, if we subtract mu1 minus mu2, is 0 among the most credible values of this parameter? Okay. It's a slightly different way of doing it, but we're talking now about what's the probability of a parameter given the data. We've reframed our question to make it a lot more kind of direct in how we think about this problem. We say, all right, given that we have our data, what's the probability that our parameters are this? And the way to do this, and I know I'm running short on time, it goes by quick. I'm just gonna do this quite quickly, probably more quickly than I'd like, but you start out with your two data points, y1 and y2, and we'll say we're getting these from, in this case, maybe a normal distribution in each one of these cases. Again, when you're doing Bayesian statistics, you make all this transparent. You have to show what you're assuming for your prior distributions, what you're assuming for how your data is actually distributed. So we're saying, all right, y1 is distributed normally. It's got a mu1 and a sigma 1. y2 is distributed normally with a mu2 sigma 2. And then we state our priors for each one of these variables. So for sigma, we think, well, I think it's going to look, it can't go less than 0, but maybe it kind of looks like this. So maybe it tails off. And maybe that's a gamma distribution. You could also just say, I think it's going to be between these two values. That would just be a uniform distribution. You can choose whatever you want it to be. And because you're stating it, you're making it transparent. It's not like there's anything, funky going on here. You can, and there are standard ways to set up your priors. Okay. So that's maybe a way we do that. And then maybe for our mu, maybe we say, all right, maybe our prior for our mu is that It's just a much wider normal distribution. And we think our mu is 100, but then, so this, our prior has a distribution. Oh, sorry, this is 2. So that's our prior for mu2. And we can do the same thing for mu1. Let's say it has some really wide prior. We say our standard deviation is this. So modeling out what you think this is going to be is very important. There's a lot more described in the resources that I'll hand off to you. And then you convert that into code. And this may look complicated, but if you see here, we see a lot of the same things that we saw in our model. We start with the same y value. Here's our mu value, our normal. That's where the data is coming from. There's our sigma value. And then our priors. Yeah, those are our 2 priors actually. So our normal and our gamma are the 2 prior functions giving us our mu and our sigma. And then this y value is being taken from a normal distribution. So when we get the result we get after all this are posteriors here. So what this is are the probability of theta1 given the data. And you can see we get a distribution of the most credible values. And that's very different from what you get with the p-value or null hypothesis significance testing or confidence interval. These are giving you the most likely values for mu1 and sigma1 based on the data. And you can get the same thing for mu2. And then you can just subtract mu2 minus mu1 to see what the most likely values are for the difference. And notice that 0 is included among the difference. So we'd say that yes, it's included. The means are not credibly different. So that's a quick example. Really went too long on part of this, so I just want to skip ahead and say that we can compare p-value to Bayesian inference and see a lot of ways in that the Bayesian inference can give you advantages. You don't have to have normality assumptions. You can accept null values. You can include prior data. It's not dependent on testing assumptions. And yeah, there's a lot of great things about it. So with that, I'm going to say that we'll hand out the code. You can walk through this a lot more slowly, and we'll have a recording of this that we can give out. You can check out some of these things again. And here are the books that I use to get all this. And you can always email me if you've got questions, if you want to try out your own data. I'd be happy to help. Be happy to help you work through it. So with that, if we got any time, if people are sticking around, love to answer any questions.
Great, thank you so much, Dr. Koebley. I will send out a recording of this talk along with the materials that Dr. Koebley is going to share, and I'll let you take that question.
Sure. Yeah, Ryan.
Don't hate me for this. How did you jump from conditional distributions to Markov chain Monte Carlo?
Yeah. So we went from here to here. Yeah, so the Monte Carlo is how you actually calculate, in this case, really it's a jump from this slide here, where we were calculating the posterior for, one specific value of your theta, right? We tried a theta of 5 for your mean and 2 for your standard deviation, okay? Problem comes when you need to test the whole space. You need to try every possible theta, or the most likely ones, and every possible sigma, or the most likely ones, given all the priors that you set up. Okay. So to do that, you need to use computers. You need to use a Markov chain. You need to use that random walk in order to test as many possible parameter combinations as you can. Does that make sense?
Yeah.
Yeah. So that's, yeah. So that helps you, that helps you get this P of D value, because basically if you test enough, you're getting closer and closer to, getting essentially getting all the possible thetas. You can never really get all the way there, right? Like there's going to be an infinite number unless you do like an analytical solution, but you can get close enough with computers that you can actually get to the true posterior.
Would you mind jumping to the next slide real quick? I know we're going to
Sure.
get it, but just
Right here?
oh, sorry, the island hop slide.
Yeah, sure.
was
The
that?
markup chain. Yeah. So again, you can imagine these islands as every possible parameter value combination. And so to find the posterior at each particular one, you have to find, you can calculate, that's what the computer does. The computer goes in and calculates the prior, and it calculates the likelihood at every single island, or at least as many as it can. And if you get enough,
And then just one more slide. I'm sorry.
Sure.
I promise last one.
That's all right. Love it.
I'm just trying to figure out how you're going from the sampling portion to the hypothesis test about the difference in means.
Sure. So right here. Yeah. I think so. This is the hypothesis. This is kind of the equivalent. Yeah, this is where we would say, if you're doing null hypothesis standardized testing, your hypothesis would be that there's, these means are the same. Or all this data was drawn from the same distribution. So the means for both of these experiments should be the same. That's your null.
Okay, so if I can just rephrase that real quick, just to make sure I got what you're saying, it would be you do a Markov chain Monte Carlo for Y1, a Markov chain Monte Carlo for Y2, and then you do a sampling of the difference of those two vectors. Am I understanding it correctly?
That's right. So the really cool thing about the Markov chain Monte Carlo analysis is that you're doing, when we look at this, maybe the model is the best way to look at this, because this is where you can imagine, this is what the code is doing. The code's starting at the top here and saying, all right, I'm just going to generate, for every one of the island walks that I'm doing, it's going to generate a different, it's going to take from the prior, from each one of these priors. So it's going to take a different value for using the prior distribution. It's going to take a different value for theta 1 and sigma 1, or sorry, mu 1 and mu 2 and sigma 2. So on the first island, it's got 4 values. And then using all that, it's going to calculate. So that's going to give it, P of theta. And then it's going to multiply by the likelihood, because it's easy to calculate the likelihood. You just plug it in. So it's going to do it for each of these 4 values that it generated randomly from each one of the prior distributions. And then it's going to go on, once it gets a result for that, probability, that posterior, it's going to go on to the next one. It's going to generate it for theta 2, which includes, a new set of parameter values. So you're going to get another probability. It's going to keep doing that. It's going to do that like 10,000 times. So drawing from each one of the priors to give you your theta, and then calculating your prior times your likelihood.
I suppose the crux of my question left is just if you're starting with Y1 bar minus Y2 bar as your prior, or if you're starting with just trying to model Y1, then model Y2, then take their difference after the fact. If you're doing,
so, okay. So let me specifically show you. So when you do this calculation, you're going to get a P of theta 1 given D, right?
Yeah.
So you're going to get a list of your final parameters. So you're going to get a mu1, sigma 1, mu2, sigma 2, all for, you know, this is in your first row of your data. So what you can do is, so then you're going to get 10,000 rows for your posterior. Can you kind of visualize that?
Yeah.
Yeah, so you're going to get 10,000 rows. For each one of these rows, you can do mu1 minus mu2. You just make a new column. All I do is subtract mu1 minus mu2 for each row, for each one of your sampling.
And then you'll do Bayes formula over the actual table that you'll get of all of the mu1s minus mu2s, and then see on average if 0 pops up.
So this table shows you the result. This table that we're visualizing is the actual posterior. So you're going to have, for mu1 minus mu2, you're going to have 10,000 rows. And that's what I'm showing you here. That's what these are.
Right.
That's just a histogram of values. And in particular, mu1 minus mu2, you can see here, that's your histogram of values. So you're going to have 10,000 of those, and this is the distribution. So you can see where the ones in the middle are your most likely islands. Those are the islands with the most people. Those are your values of mu2 minus mu1 that are most likely.
Got it. Thank you.
Yeah, great questions. This is really, to be honest, this is probably not an hour talk. This should probably be a little longer, but I wanted to give as much of a basis as I could. And the vocab is so important with this stuff. So hopefully it gives a bit of a taste that we can look into those references. And again, here's my email. If you guys want to try this with your own data, or you have questions about sources of other sources you can look into, ways of setting up different types of tests, I would be happy to help. So there's a lot you can do. You can do a lot of really complicated testing. Any more questions?